Revati madam, please text in the chat box because the next session.
Okay, I will request all the participants to mute themselves. Satvik, sir, kindly mute yourself. Can anyone? Yeah. Thank you. Thank you, participants, for joining us. Now we are moving ahead for our next session, and the next session is about energy efficient cooling strategies in the canopy layer, a case study approach for UHI mitigation. So our next speaker is Dr. Fayaz Ahmed sir. I would like to introduce him. So Dr. Fayaz Ahmed sir is an faculty in Department of Architecture at the School of Planning and Architecture, Vijayawada, an institute of national importance under the Ministry of Education, Government of India. He holds a PhD in Architecture and Planning from Anna University, Chennai, along with an M.Plan, MS France, and BArch from reputed institution. His areas of expertise include urban microclimate, 3D city modeling and simulation, building and urban physics, geospatial analysis, thermal comfort, and energy efficiency. He has over a decade of teaching, research, and consultancy experience and has co-funded Formation Studio for Architectural Practice. Dr. Faz is the project director of ICSSR funded project on post-tsunami housing reconstruction and livelihood revitalization in vulnerable Indian coast. He is also a principal investigator for Government of India project on cooling strategies for Hyderabad to mitigate urban heat island effects under the Amrit scheme. Internationally, he has contributed as co-investigator in the CREST project funded by the British Council and as member in EU-funded REUCOM project on resilient urban communities. His publications record is extensive with contribution to reputed journals like Nature, Communication, Earth and Environment, Urban Climate, Land Use Policy, and international conferences including ICUC and IDRIM. He has supervised doctoral research in areas such as outdoor learning environments, flood-sensitive planning, and urban soundscape, and has organized national and international conferences at SPA Vijayawada. He is recognized with several awards and fellowship also. Well, I would like to welcome Dr. Fayaz for the next session. Welcome, sir.
Thank you, Dr. Prashanti. Am I audible and clear?
Yeah, you are audible.
Thank you. Let me share the screen. Please give me a confirmation. You can see my screen.
Yeah.
Okay. Yeah. First of all, I would like to thank Vijay Lakshmi ma'am for the opportunity, and it is indeed an eye opener for me as well. And there are a lot of things that I've also understood in these sessions from Professor Matt. And what I'm going to present today is one of the projects that we are working on. It's called just a second. Yeah, we are calling it as cooling strategies for Hyderabad, and this is one of the projects funded under Atal Mission for Regeneration under Center for Excellence here in SPA Vijayawada. And I'm leading the team, and we have other members as well who have contributed significantly to put up all this that we have understood, that we are presenting it to the Hyderabad city. Okay, the structure of the presentation, I'm to keep it in brief. We'll just very briefly discuss what is the context in which we are trying to address this issue, and what is the key objective of this project, and how we have approached this project, and how we approach this in Indian context, and what city planners do, and how this is slightly different from the approach that we conventionally do in the Indian cases. I'll be highlighting that, and we tried to integrate both surface temperature and air temperature. And I think in the last lectures as well, in the first lecture, there was a lot of discussion about how we can, how we have to look at both things together. And we have developed, we have tested several strategies that is available in this context, and we came out with some solution metrics that can be implemented. There are strategies that did not work, and there are strategies that which worked, and there are strategies which worked but very minimal impact. And the last lecture has given me some more confidence to present the outputs in a way, because some of the strategies which we did not give any result. So when we presented that in a bigger forum, we had some critical issues on that. Anyway, so what is the background? The case is Hyderabad, and we have experienced the temperature rising more than 40°C on several days and so on. And also the build-up has increased significantly over a period of time. So, and persistent night heating and UHI has been well documented, and is one of the problems that has been there for quite a long time. And this has been a case in other cities as well, in other Indian cities as well. And we are quite familiar with this kind of issue. Okay, first thing is we are trying to discuss this under a broader aspect, what has happened over a period of time. But if you take out the data from 1970s to till 2024, we're just trying to plot. If you take the anomalies, there has been only a slight increase in the overall temperature, an average, if you see. But if you see the data closely, the summers have been much severe in the recent past, and this was also pointed out in the first lecture by Professor Matt on how this has been recorded in other cities as well. So if you look at the broad spectrum, this is for Hyderabad case only. The net increase is not so significant, but if you look at the summer, the intensity of summer, or the frequency of heat waves that has occurred, that is quite severe. This is first point that I would like to place here. The second thing is, if you put the temperature and the humidity data together, and of course we have severe summers. Okay, that's known fact. And what we also observe is, in addition to the higher temperature, we also have a low humidity that is happening that is observed in Hyderabad case. And in the morning session also, and this was referenced, how low humidity can have a more impact other than just drier air, or other than just drier temperature. It will have an impact on how vegetation also works. So this is something which is also something that we have to look in. It's not only about the temperature, and we should also look at how the humidity plays around. And this is only with respect to the summer time. But if you look at the other time, there are cases where the humidity raises to 80, 85, 90 in touches and all. So we are trying to discuss more on how do we address the issue of heat during the summer months. So this is second thing. The third thing is, what is the objective of this project that we are trying to do is to develop an evidence-based strategies that can be implemented in Hyderabad. So with which we went around to identify some of the hotspots of the city. I'll present to you how those hotspots have been identified, and we approached after identifying hotspot. We wanted to understand how the heterogeneity in the city works, and like Professor pointed out, within the city we'll have different urban settings, different greeneries, different water body combinations, and so on. So how do we identify that different characteristics within the city, and how do we arrive at how do we arrive at the strategies that may work for those heterogeneous urban environment? This is the overall methodology that we have tested, and once we have these strategies in place, and we have developed some metrics that the Hyderabad city can implement in coming years. Okay, what is the conventional way of approaching this subject is to identify hotspots and identify the UHI intensities. And most of the time, we have seen that the city planners use Landsat data, MODIS data to understand how these UHI intensities can be measured. And most of the time, it is the surface temperature that we record and compare. And one of the common things that we try to do is to map how the building density has changed over a period of time, how the vegetation index in terms of NDVI, how it has changed over a period of time. So this was also pointed out in the morning, how the NDVI index can be used as one of the measurables to check where are greens and what are the cooling potentials of these NDVI. Similarly, what we also do is to understand the land surface temperature. This was also pointed out in the second day or so, where how these surface temperature can give a lot of insight on what's happening in different parts of the city. And most of the time, what we do is we use this and then arrive at the hotspots and the UHI intensities across the city. So this is one of the steps that we also tried to do in case of Hyderabad, and we came out with what are the hotspots and what is the UHI intensity for last 2-3 decades. In addition to that, if you see, this is daytime temperature. Okay, let's be clear. The surface temperature that I'm trying to put up here is the daytime temperature. But what happens to the temperature during the night time? That's also something that we have to understand, right? So we use MODIS data to understand how these temperature, what is the thermal environment during the night time. So if you look at these slides for 2004, 2014, and 2024, during the daytime, during the afternoon hours, and also during the night time, we mapped the changes in the temperature profile across the city. And you can also see the difference in terms of year. For example, in 10 years, you can see how the change has occurred in terms of the temperature across the city, and what is the intensity of these temperature during the city during this period. And same happens during the night time as well. You can see the concentration of heat at 10 p.m. Concentration of heat in the later night as well. This is one thing. Second thing, if you see on the right hand side, I have put up the sections through the city, just to understand what happens. It's not uniform throughout the city. Right? There is variations in the surface temperature also across the city, depending on the build form that we have, depending on the vegetation cover that we have, depending on the water bodies that we have. So the urban heterogeneity also plays a big role in how we understand the heat that is there in the city. So this is second point. So in the first thing, we use Landsat. In the second layer, we try to document these thermal variations during nighttime using MODIS data. And in addition to that, we also took the live data, meaning the automatic weather station data from Hyderabad city. Fortunately, there were about 150 weather stations in the city. of Hyderabad. So we could purchase these data to from different. These are the different weather stations from which we have taken the data, live data, and then we used it for validation of our work. And this was also again pointed out by Professor in the lecture that the reliability of ground level data becomes very essential to say something which can be as realistic as possible. So we have taken some data about 17 weather stations within the city of Hyderabad and to on various variables to document it. So some data that I have just plotted here, 2014-24. What is the variation in the temperature for the same day in 2014 and for the same day in 2024? Okay, so how the concentration of these islands are changing, especially in a decadal time. So we have three results now. One using the air temperature, the metro, the automatic weather station data, AWS data, and then the Moody's data and the Landsat data. And if you look at the result, we could find a variation in the air temperature by about 2.7 degrees Celsius. But if you look at the Moody's data, we could find the UHI intensity of about 6 degrees Celsius. And if you look at the Landsat data, we were able to compute the UHI intensity of about 9 degrees Celsius. So on an average, there is an UHI intensity of 3 to 8 degree difference across the city. Now, how do we capture these variations across the city? For example, like I have been saying that if you take out a section across the city, because of the different urban heterogeneity or urban density, green cover and blue cover, the surface temperature varies. But this is Hussain Sagar Lake. For the ones who are not aware of the geography of Hyderabad, this is one of the lakes, famous lake. You can see how water body can bring in the surface temperature down by significantly. This can you can see there is a difference. There's a dip in surface temperature. Also, you can see because of the green cover how the variations can also be brought. This is understandable, green and blue. But if you look at the urban fabric, also there is a variations within the city. So how do we capture these variations and how do we map this urban microclimate conditions within the city is something that we wanted to try. So in the second objective or in the second layer, we wanted to capture how these variations occurs in a canopy layer and how local climate zones can be identified within the city so that we can develop some strategies that are very, very specific to those neighborhoods, not the generalized strategy for the entire city. So if you look at the theory also, if you imagine if this is the entire city and if you zoom to one of the urban areas, you can find that you have buildings, vegetation, we have narrow streets, wider streets, and so on and so forth. Okay, so this is in a technical way, these are called local climate zones, right? Local scales. And as architects, what we are interested in buildings and the immediate context of the building. But all these fits in the entire city fabric. So from the theory, from theories and from other studies as well, the urban morphology plays a vital role, or it has a significant impact on how these strategies going to work. And also, not all, there's no one solution to all. This has been repeatedly been mentioned and presented in the last 4 days as well. The solution has to be tailor made. It has to be specific to the urban areas that we have. So we also wanted to adapt a similar strategy in our project to arrive at more context-specific solutions. And why do we do that? And do we have supporting arguments for this? This has been again well documented in other literatures as well. A lot of studies have shown that UHI intensities are found much severe. UHI intensities are found in LCZ 2 and 3 categories, which are compact mid-rise and compact low-rise categories. And at the same time, a lot of solutions have also been worked out for these specific LCZs. So, in addition to that, we can, once we are able to identify what are the different the climate zones that we have within the city, we can also map what kind of strategies may best suit for those climate zones within the city. We are not talking about the bigger area in general, but within the city, if we are able to identify what are these, how these local climate zones are formed, and how once we are able to identify such local climate zones, we will be able to suggest an appropriate strategy that may work in those local climate zones. So we adapted, again, this is a well-established process in the literature. We can divide the city into 10 urban fabrics and 4 vegetation fabrics and 2 lands and water body. So like we do land use classification, we have to do this kind of classification for the city fabric. What are the properties that is used for classifying? It takes into account your sky view factor, canyon street aspect ratio, mean building height, your terrain roughness, building surface fraction, impervious area, pervious area, and surface albedo, and also anthropogenic heat into the context. So when we divide these the city into the local climate zone using these variable, we'll be able to understand the city in terms of the microclimate formation, and probably come out with strategies that may work appropriately for that. So what is the result that we got in classification? You can see this is for the entire city of Hyderabad. We found LCZ2 about 76 square kilometers of built area falls under LCZ2 category. LCZ2 is compact mid-rise, and LCZ3 is 100, more than 100 square kilometers of built up area falls under compact low-rise category. So if you are able to come out with some strategies that that contributes, that forms major portion of the city, probably we'll be able to. We are trying to address a major part of the city fabric. What we did is we did not give solutions to the entire city. We wanted to identify a hotspot within the entire city, and wanted to demonstrate in one of the wards, one of the area of interest, which included 3 wards, to come out with strategies that can work in this particular area. So if you this is one of the this is the area of study. This is the area of focus where we have tested all the strategies that we wanted to apply for the entire city of Hyderabad. So we have the LCZ classification for our area of interest, and we have documented all the building fabric of different land uses that you can see here. If you look at this here, in terms of local climate zone classification, these are the different types of local climate zones that we can observe in our area of interest, and these are different neighborhoods that we have identified, where we have went into details and documented those neighborhoods, and then tested our strategies. And what are the strategies that we have tested? This is another thing that requires discussion. Based on the case studies and based on the several case studies that has been tested on this line, we wanted to test how green roof works, how green wall works, how what is the street tree combinations that we should have, roadside vegetation, pocket green, all of it what was discussed in the morning. A lot of things have been said in the morning as well. We wanted to check how this can be integrated in a more meaningful way. And it's not something new that we are trying. This has been tested in other cities like Mumbai, Chennai also. What results that they have got, and can we come out with some can these strategies again work? So when we say vegetation, we wanted to try several uh, ways in which vegetations can be integrated into the city fabric. One. The second one is the blue infrastructure. Like I said, although this is a composite climate, the climate of Hyderabad, but during the summer it becomes very very dry. And I also showed in the beginning that the humidity level goes down below 20, and the air becomes very very dry. So we need some humidity, and again, this is something that adds value to what I've been saying. That vegetation also requires water, like Professor said in the morning. Where though we may have a good vegetation, maybe if we have a low humidity, and if the air is dry, and these vegetation may not work. So particularly in case of Hyderabad, when we did an assessment, and we found that this issue also has to be addressed. It's like a desert climate during summer months. Okay, at least for 1 month, we have such a situation. That also has to be understood, and we need some strategy that can work for that particular. Of course, it is a seasonal intervention, but we think that that needs to be addressed as well. So we tried fountains and misting systems in the model to check whether we can get some benefit out of this. And the third strategy that we tried is, of course, a cool roof, cool paints, and cool pavements of different varieties on the roof, on the pavements, on the walls, and the facades that we have tested these combinations. And these are applicable in existing case as well. All these three strategies can be tested in existing case. And we also came out with some strategy that can be applied in the new case. For example, let's say what should be the aspect ratio, sky view factor, building height, and what could be an ideal orientation if a new city is being developed. Actually, in Hyderabad, there is a commissioner, or there is an commissioner set up for future cities. They are coming out with a new layout, new city formation, where they are trying to push or create a new city formation in some parts of the city. So these ideas can also be taken into implementation in new development or greenfield development. In addition to that, several studies in India have shown how shading can help in a large way. Okay, these are very simple strategies that can be tested, and it has been tested in several cities as well. Shading can help in a long way, at least during these summer months. Okay, so what we did, we used environment simulation for all this modeling, and we also had taken our mobile weather stations to collect primary data, and of course we have used extensive data from the local automatic weather stations across 155 weather stations the Hyderabad city has. Okay, so what are our samples? For example, let's say if you take out one urban area of about 40,000 square meters, it's about 200 meters by 200 meters we have taken for modeling. And you can look at the variations in the urban areas, the characteristics of urban form. One urban form is not same as the other. Okay, all these six images that you see is of same area within the city of Hyderabad. So we can't have the same strategy here, same strategy here, same strategy here. So that's the idea that we wanted to bring in, and we wanted to check what are the combinations of strategies that can be suggested if you have high heterogeneous urban environments like you see here. So we went down to map the areas and developed models, and then these are some of the settings that under which all the simulations have been read. And we have used NVMet where we can simulate about 52 variables of different characteristics, including air temperature, mean radiant temperature, surface temperature, relative humidity, and PET, SET. So a lot of variables can be taken up, and a lot of things can be simulated using this. And one of the index that we have used to compare all our results is PET. Although we can use other parameters, PET is one of the parameters that has been tested, and in several literatures we found that the reduction in terms of PET, because we are trying to measure at 1.2 meters level. So we wanted to make sure that this is perception of heat at 1.2 meter is checked. We could have done this at air temperature or surface temperature as well, but we restricted to the PET, SET, UTCI values as well. We do have comparison with air temperature, but the result that I'll be presenting will be by keeping PET as the common denominator for a comparison. So some initial results, I think you guys must be aware how the NVMet results are generated. Before we actually go into the strategies results, one of the thing that we should also get an understanding is how these strategies will have an impact on indoor conditions also. Okay, this has been pointed out in the presentations as well. Whatever we do in the outdoor environment have great implications on how the indoor conditions are framed, how the energy consumptions are being made in indoor conditions as well. So to do the concretization of that statement, we have two graphs that you can see. Both are taken from the same study area, just to demonstrate why the strategies in the outdoor environment have a profound impact on what happens inside. So on the left hand side we have a residential building, okay, and the right hand side we have commercial building. You can see here. So these are surface temperature. This is air temperature, surface temperature, air temperature, and this is indoor air temperature. The bottommost third line that you see is indoor air temperature. What happens? This is a glass building. You can see this is building B. This is a glass building. This is a typical apartment building with conventional windows that we have. What is the difference here? You can see that in case of the apartment building with a typical window size, and that we have it like in most of our Indian cities. What happens to the indoor temperature? You can see the peak indoor temperature reaches during the evenings, about 6 or 7 in the evening. You can see that the temperature reaches to about 36 degrees or so. Okay, whereas your glass building, what you see here, your 36 degree or the indoor temperature that we see here that happens in the evening comes or reaches the building, the indoor temperature, ambient temperature reaches to about 36 degree even in the morning itself. Why? Because of the poor choice of material that we have that we have in our building. Okay, it's not only about how we do, what kind of strategies that we work in the outdoor condition. It also matters how we use these materials, how we select the building materials, how we select the building materials for the glass, roof, and windows as well. A lot of it has been discussed in a very, very detailed manner in last several sessions. Okay. Another thing that we have to understand is when we apply strategy, some strategy may give result, some strategy may create problems. And I'm happy to be confidently presenting this now because I can see that this is not something new that we got. Some strategies are giving negative results, although this has been promoted as the best results possible. So, for example, let's see here, we have three things plotted. This is one is existing case, the other one with a cool roof, and the other one is with a cool payment. So what happens? We have potential air temperature and potential air temperature for the base case, potential air temperature for the cool roof case, potential air temperature for combination of cool roof and cool pavement. So which is the orange line that you see here. I think that's not much of a variations that you can see in terms of air temperature in all three cases. But there is a difference, 1 degree difference that has been that itself is a significant contribution. But we will come to this later. But if you see, if you go only by this parameter, we may be trapped. We may have a negative, or we may have wrong conclusions by looking at only this parameter. However, if you see the other parameters, for example, let's say mean radiant temperature. You can see this is the mean radiant temperature, and you can see if you use this is base case and the cool roof case. This is base case and base case plus cool roof plus cool pavement. So there is an increase in mean radiant temperature. Okay, so maybe it is helping in one way, but it is creating a problem in another way. So this has to be we have to see the impact in a clean manner, and then we can say whether the strategy may work or may not work. If you go only by temperature, or if you go only by MRT, or if you go only by other parameters, we may end up suggesting something which is good for in one aspect, it may not be good in other aspect. This again, for example, let's say I've been saying humidity is a cause of concern for Hyderabad case, particularly in summers. But if you, for example, let's say this is humidity level in an existing case, which is about 25%, which itself is low. But if you use the combination of cool roof and cool pavement, the humidity level goes further down. So here it is a problem. Even if you use this it may have a beneficial impact, but we are also creating some kind of other problem that also should be kept in mind when we suggest something in specific. Okay, so like this, we did an assessment for 13 different neighborhoods within the area of interest that we have identified. 13 neighborhoods have been modeled like this, and all the simulations have been done for these 13 neighborhoods. And we did a comparative assessment of all the parameters starting from impervious surface area, pervious surface area, and what is the building density, in all that. Most of our comparison will be on PET and surface PET only to check what is the variations that we are getting in implementing some or several of these strategies. Okay, and that is with respect to the entire neighborhood. We also took a street as an element, and then we wanted to do interventions on certain streets which are commercial, which are frequented by pedestrians. And how do we bring comfort at pedestrian level by having some intervention that is very, very specific to the street combination. So we identified a street, and we did, of course, we did a simulation, and we also took several measurements during the summer months to check what is the validation of the simulation and also the measurements that we have taken on ground. What are the strategies that we tested for street? This is the base case, and in addition to the base case, we wanted to add trees. For example, let's say 50% of the trees, meaning trees at 7 meters distance without touching the canopy layer. trees which are just touching the canopy layer. It's not overlapping canopy layer. And ground cover, if we there's a lot of fascination for suggesting ground covers for improving, for doing the beautification of the city. You must have seen in several cities, especially the roads which is leading to airport. This kind of interventions has been pushed from the government, and we try to implement it. So what is the impact it is going to create? And if we go only by shrubs, not by mature trees, what is the impact it is going to create? And we have seen from the other studies also that shading can give a lot of relief, particularly in junctions. So how do we bring in shading in the street so that we can extract some benefit out of it? And of course, all different materials, pervious materials, reflective coatings have been tested. Okay, so in summary, what are the strategies that we wanted to test? What we have tested is cool roof as one of the strategy, cool pavement as one of the strategy, cool roof and cool pavement together as a strategy. Why this combination? Sir pointed out in one of the discussions that if you have high-rise building, maybe this combination is not okay. Okay, the effectiveness of a cool roof is limited to a certain level. But whereas if you see the case of Hyderabad, it is mostly compact low-rise or compact mid-rise. So where we can have a combination of both your cool roof and also cool pavement in low-rise areas. So we made a combination of strategy to check whether this can work, and we also tested pervious pavements, and we also applied in addition to cool roof plus cool pavement, we also added cool wall in southern wall in only on southern wall based on the solar radiation studies that was done to whether this can also help in certain way. And of course, we tried with water body, and in the new layout, what is the impact of orientation that's going to create. And also in the morning, also it was pointed out, having green pockets can be an effective strategy. So introducing a green pockets, not like a large one city level parks, rather than having a micro green urban pockets can be beneficial. So we check that as well to see what is the output that we are trying to what is the output that we may expect if we implement this. In addition to this, we also tried green roof. There was some discussion about green roof as well in the morning, and it is of course a very cost intense strategy, not cost effective strategy. Similarly with green walls as well, these are maybe for like affluents. So and sunshade as a shading strategy, and a lot of combinations of trees and vegetations to check which combinations may work in these neighborhoods. So these strategies were applied to the building model that we have taken for all the 13 neighborhoods. This has been all these strategies have been applied. So we'll quickly see some of the results for each of the strategy. I'll not go into details of each of the results, but I'll just highlight some strategy in each of the neighborhood, and I'll just very quickly go through which worked, which did not work. For example, let's say this is one of the neighborhoods in the Hyderabad. You can see this is the base case. How do we read this graph? You have a base case here. This is existing case. The first assessment was done to analyze what is the existing case. So keeping that as a zero as a reference, these strategies are added. If we add cool roof, we got a PET reduction of about 0.16 degree difference. So if we added cool roof plus cool pavement, the PET decreased by see here when I say decrease and increase, I think we should understand this is from the positive aspect. Okay, so there's an improvement in the cooling by about 0.35 degree difference. But if you see if you apply only cool pavement, the PET value decreased. It added to discomfort. Similarly, if we see here, the trees, when we added trees and also all your cool roof and cool pavement and greenery, it actually added to the discomfort. So what was the most effective strategy that worked in this case was cool roof plus cool pavement and green roof, with which we were able to bring the PET value by another zero 0.5 degree difference. And if we apply only green roof and cool roof plus cool pavement, we were getting an PET reduction of about 0.3 to 0.35 reference. Similarly, if you see in other neighborhoods, the only strategy that worked was cool roof and green roof and green floor. Here means the ground cover that we had applied. So whereas if you apply other strategies, we found that the PET values it did not improve. It actually caused more discomfort when we apply these strategies. So these strategies were not effective in this area. Similarly, if you in one of the neighborhoods when we tested, none of the strategy gave any. None of the strategy were effective. In fact, it increased the PET value by 2 to 3 degree Celsius. Okay, so in this neighborhood, we're trying to find out what could be the reason and what has gone wrong in this case. Similarly, in other case also, when we applied all the strategies, none of the strategies gave an improvement from the existing case. Okay, so maybe from what I was Sir said in the morning, even I'm now thinking whether it is because of too much of dryness in the air or the other things. We need more data to explain why this is happening. This second thing. In other strategies, we can see similarly we were able to get some benefit by appropriate placement of trees and vegetation, and some impact on greenery. Similarly, like this, we did for all the 13 neighborhoods that we have identified. In some neighborhoods, we were getting results, improved results in PET for all strategies. Although this may be very fractional, there is slight improvement in PET values by adapting all these strategies. For example, in other neighborhoods as well, you can see a lot of strategies, a lot of combination of strategies or individual strategies seems to work in this particular case, especially in this case where you have LCZ4. A lot of strategies, in fact, all strategies gave a positive output from 0.8 to about 2.5 degree reduction in PET values. Like this, we did for all the 13 neighborhoods that we have studied. What is the overall observation from, these are from the neighborhood study, and some observations, overall observations from the street level interventions. I've put up a matrix here. How do we read this matrix? We have, this is for vegetation, and we have parameters for comparison here: air temperature, relative humidity, MRT, UTCI, and PET values. On this side, we have the strategies, which was by having only trees, what is the impact it is going to create? By having trees plus ground cover, what is the impact it is going to create? By having 50% trees and ground cover and shrub, what is the impact it is going to create? Here, 100% trees means trees at a 7-meter distance. Okay, and this is much further than that. And we have only ground cover, and this is the base case for comparison. So if you see here, if you go by only trees, we can improve. We were able to find from the simulation results that there's an improvement in PET value by about 2.5 degrees Celsius, and also you can see there's an increase in RH value, which is also required in case of Hyderabad, particularly during the summer months. Okay, And also, if you see in other strategies, we can see some improvement in PET value. But whereas in other, only for ground cover and shrubs, the results were not that significant in thing. Other thing that we should also we found is the MRT value also should be low. We were trying to be sure not it's not only about PET, the MRT value, the reflected heat also should be low. So vegetation had that impact that we can see from here. And when it comes to the temperature, we could find about 2.5 degree reduction in air temperature, and when we use trees, and you can see the other results here. This is for the vegetation, and this is for the surface. Although these are the combinations of strategies that you can see here, and you can see there's an improvement in PET by about 1.5 degree Celsius. But although there's an increase in benefit in terms of PET value, but there is a significant increase in RH value, and also you can see there's an increase in MRT value. Okay, so these strategies are making the environment more drier, and which is also not good, as we have been pointed out. Okay, other strategy that could work in the street was the shading. Shading gave a significant improvement in the PET values, where about 4 degree difference or 4 degree improvement in PET values we were able to observe. And when I compare with other index, UTCI gave a significantly higher numbers. Since we are using PET value, we are trying to discuss only the PET values here. And also the other impact, other thing that should be kept in mind is it also brought down your MRT value by significant number. Okay, it's not only improved your PET value, it also brought down your MRT value. So when this is for the strategy, shading strategy. And when it comes to water body also brought in a significant impact in PET values. It improved the PET value by a big number, and of course it has increased the RH value. And we wanted it also, and this is what we wanted when we at least during the summer months, seasonal months, we wanted to improve slightly the humidity levels there. We don't want the air to be much drier. We wanted that to be improved so that the breathing can be easier. And now I understand from the morning session that this is also good for the trees. They will also be more effective if there's water content in the air. More air, water content in the air. Okay, so what is the overall conclusion from the study that have been done? We have come out with all these strategies that you can see here. What is the impact that it has created in terms of air temperature? We could see a reduction of air temperature of about 0.8 to 2 degree difference in terms of the materials that we have used, and we got a slightly improved result in terms of air temperature when it comes to the trees. And these are overall conclusion. How we are presenting it to the municipality, because we are closely working with the local government to implement this in city. So, for example, let's say cool roof. It can be a passive strategy, how it is applied and what is the impact it is going to create, and by what means. So one of the reasons I also asked this question is we have to convey this to the decision makers. Decision makers are not happy with improvement in 0.8 or 1 degree improvement in temperature. What is 1 degree? How does it matter is the question that we get to hear. So if we say 10 degree improvement, that's substantial. They look at it in that way. But hardly we could see an improvement of about 1 degree or 1.5 degree is what we were able to observe. So instead of conveying like this, we thought we should write it down and say what is it happening, why those strategies are working better, and in what way this can be improvised. So we came out with a matrix as well. These are supposed to be the strategies used in the neighborhoods. So all the neighborhoods that has been studied has been mapped here, and all the strategies that we have tested has been listed here. So which strategy worked, which strategy was more effective, less effective, and for which some of the strategies we did not try. So that has been mentioned here. Finally, we are giving this as an output on neighborhood level interventions that the city can adapt. So, based like I said, they don't understand the. Finally, the decision maker has to understand this. So they don't understand these numbers. So it has to be conveyed in a simple way, so that some of these strategies can be implemented. Okay, so for all 13 neighborhoods, we are coming out with a simplified representation of how these strategies can work and where these strategies can be implemented in that particular neighborhood. Like this, we have developed for all the 13 neighborhoods, and we have a landscape architect in our team. So he has developed context-specific landscapes, right from trees to shrubs and ground covers, which requires minimal maintenance and less water requirement, and which survives in such conditions. That has been developed, and we'll be presenting it to the municipalities. As an experimental pilot project, we are suggesting that the city can implement these three strategies in coming summer to check to check its impact, and if the results are good, the same can be replicated and applied in other parts of the city as well. So we had presented this to the municipalities for taking up in for further implementation. Thank you so much for listening. If you want to know a little bit more about the project, we have created a spatial data infrastructure based on the results that we have generated. You can log in and check here. Thank you.
Thank you, Dr. Faiz. Thank you so much for that wonderful presentation. Since we are 5 minutes behind, I think we should start with the next presentation. So, can we have Dr. Lily? Are you here? Yeah, she's there. So, please introduce her.
After the wonderful session of Dr. Faiz, now we are moving ahead for another session from Dr. Lily Rose. So her topic is thermal comfort and heat stress in outdoor urban environments, challenges and design implication. Now I would like to introduce our speaker. So Dr. Lily Rose is a distinguished academic and researcher with over 23 years of teaching and research experience in architecture and climate responsive design. She earned her PhD in architecture from the Faculty of Architecture and Planning, Anna University, with a specialization in urban heat island and thermal comfort studies in the Chennai metropolitan area. She holds a master's architecture and bachelor's architecture along with a graduate diploma in construction project management from NICMAR, Pune. Her research interests span urban climate mapping, thermal comfort simulation and analysis, local climate zone mapping, sustainable design, vernacular architecture and conservation. She has presented her research in prestigious international forums including ICUC, ISBE, IFOU, APSA at the World Sustainable Building Conference. Dr. Lily Rose has received international recognition including with William P. Lowry Student Travel Award and the IAUC Conference Award sponsored by the European Space Agency, Japan. With an impressive academic record, she has published around 40 research articles, more than that I think, in reputed journals and conference proceeding. She also sought after expert speaker, having delivered invited lecture at NIASA FDPs. And beyond teaching and research, she has actively contributed to the profession by organizing FDPs in association with Council of Architecture and Intact Heritage. She is associated with multiple professional bodies and editorial boards, including being an active member of the International Association of Urban Climate, Global Outdoor Thermal Comfort Studies Working Group, and the life member of INTAC and the Indian Society of Remote Sensing. Presently, she is working as Dean Academic in SPA Vijayawada. Now, I would love to call Dr. Lily Rose ma'am to deliver her session. Thank you, ma'am.
Thank you, Dr. Prashanti. I think after Professor Matt's session for the past 4 days, I think whatever I'll be presenting today is just a drop in the ocean. But still, we have done few of such studies in Indian cities. I'll be presenting that. Let me just present my screen. I hope my screen is visible to everyone. Dr. Prashanti, am I audible? And
Yeah, now it's visible.
Yeah, ma'am. It is audible.
Thank you. So today I'll be just giving an overview of this thermal comfort studies, outdoor, especially focusing on outdoor thermal comfort studies that have been done in few of the Indian cities. To start with, I think all these have been discussed earlier as thermal comfort differs, the indoor thermal comfort differs with that of the outdoor thermal comfort, and most of it depend on the personal parameters and the meteorological parameters. So the parameters that are used basically as I think Professor Aya Vijayalakshmi had given a list of indices that are used both in indoor and outdoor thermal comfort studies. So this basically most of the studies are pertaining commonly used are PMV, PET, PIT and other things. So here we'll be focusing on all this. Why this is important is basically these studies would enhance the productivity. It has a significant impact on health. So we do have these thermal comfort affects the productivity, it affects the performance, it affects the learning and cognitive skills, health and well-being. So it is important in those. Just to give a brief on why indoor and outdoor are different. Indoor studies wherein we can have controlled temperature, controlled humidity. It's basically a steady state affair wherein all the indoor parameters can be controlled, and in the absence of direct solar radiation, wherein when it comes to outdoor comfort, it is very difficult because you cannot predict the outdoor state of environment. It is not in a steady state condition, and it depends. It also varies in terms of the expectation of individuals, and there are three basic parameters which differentiate indoor to outdoor conditions. Basically, in terms of physiological aspect, that is in terms of our adaptive nature, especially people tolerate a larger variation in climatic conditions in the outdoors when compared to indoors. Though we have been in India, we follow that somewhere around 24 to 28 or 24 to 30 degrees is a comfortable range when it comes to indoors. But then in terms of outdoors, we do tolerate up to 32 degrees, depending on the geographical region where the city is located. And there is also this thermophysiological aspect, which also affects basically based on your clothing level and based on the activity level. Suppose even during daytime, during hot summer day, we do see cricket matches which are being conducted in the afternoon because their expectation is different, their mental state is different. So in all aspects, so the comfort ranges vary depending on the activity you perform. Then the steady state condition, which is basically the heat balance. So the outdoor comfort ranges are much wider when compared to the indoor comfort ranges. So these basically affects the activities that are performed in the outdoors. When it comes to necessary activities, irrespective of the outdoor condition, whether it is good or poor, we do perform the necessary activities. But when it comes to optional activities, it is significantly reduced when the quality of the outdoor environment and the comfort conditions are not appropriate. The optional activities are reduced significantly, but if it is enhanced, then the optional activities enhances. And there is minor variation in terms of social activity. So these uncomfortable outdoor environments results in spending less time in outdoor, and we hardly see people in the outdoors during daytime, and it reduces the social activities and also reduces the optional activities of visit to cafes or restaurants or any other outdoor spaces um, in terms of leisure or recreation. So to give a brief thing, in terms of indoor thermal comfort, the variation in terms of meteorological parameters are the ranges are quite less. If you see the diurnal variation in indoor and compare that with outdoor, the diurnal variations are much higher in outdoor. So if you see here, basically we can see that the temperature varies. Sorry. So you can see the temperature varies from about 31 degrees to about 27 degrees. So there is a variation of about 4-degree variation. Similarly, there is a variation in terms of from about 23 percentage to about, from about 18 percentage to about 67 or 70 percentage of relative humidity. So these variations would create a different kind of thermal feeling or thermal sensation of in the human being. So basically, if you see, you can see within outdoor space, within a short space, spatial region, in terms of if you stand in between two buildings, there can be heavy wind speed, but if you just go to the street, the wind conditions completely differ. Similarly, you, standing under the shade, the comfort condition differs. Standing directly under the sun, the comfort condition differs. So there is a lot of spatial variation in the outdoor condition when compared to indoor. So these temporal and spatial variation creates different kind of thermal perception and thermal sensation in the outdoors. And also the wind conditions. So in the indoors, anything beyond 1 or 1.5, people cannot withstand, and they find it quite uncomfortable. But in the outdoors, people can withstand ranging from about 2.5 meter per second wind speed to about 10 meter per second wind speed. So it depends on what activity you are performing, your comfort conditions differs. So when you're performing fast walking or when you perform jogging, you can even withstand a wind speed up to about 8 to 9 meters per second. But if you're just relaxing, if you're just sitting, then you can withstand up to about 2.5 meters per second. So this is the kind of variation in terms of wind speed that we feel or that we perceive in the outdoors. So to give a brief on again, depending on the latitude, depending on the dry bulb temperature, relative humidity and wind speed, our comfort perception or sensation differs. This is an example of how the temperature and humidity behaves and how they yield to comfort conditions. If you see, this is in Lund, Sweden, wherein the dry bulb temperature variations are between 17 degrees Celsius to about 2 degrees Celsius, ranging from summer to winter. But you can see the relative humidity percentages that varies from about 66% to about 91%. So the relative humidity is quite high, but then we will not feel uncomfortable because the temperatures hardly crosses 20 degrees Celsius. Though the relative humidity is high, at lower temperatures, we won't feel very humid and it may not have a negative impact on the comfort condition. And you can also see that wind speeds here are quite high, ranging from 3 to 4 meters per second. So here, it is the wind chill index that matters a lot rather than the humidex index that creates uncomfort feeling as such. So here if you see, this is the comfort condition. So you can see these these areas where you feel uncomfortable are mainly due to the higher wind speeds and not because of the higher humidity. Though the humidity is quite high here, The discomfort is mainly due to the wind speed and the temperatures and not because of humidity. Where in the same case, it was this is in case of Vijayawada. So all three examples that I've chosen are humid conditions. But then the first one is cold, humid. Here, this is hot and humid. You can see the temperature here ranges between 30, the maximum temperature is somewhere around 32 degrees and the minimum temperature is about 24 degrees. So we just have roughly around 8-degree variation between winter and summer. But the humidity ranges, if you see, it ranges from about 61% to about 81%. So though the humidity is lesser when compared to Lund, which is a cold, humid place, here the issue in terms of comfort is mainly due to the humidity and higher temperature. So the high temperature and higher humidity is causing the discomfort. And you can also see that temperatures here, the wind speed is hardly 1 to 2 meters per second. So the wind speed is lesser. The discomfort is mainly due to the higher temperatures and higher level of humidity. So here we can see these humidities, especially the temperature ranges. If you see here, it is somewhere around 22 degrees Celsius to around 26 degrees Celsius. Even at that particular 22 or 26 degrees Celsius, we would find discomfort mainly because of higher humidities ranging at around 70% or 80%. This would cause a lot of discomfort in terms of outdoor conditions. So this is another place. This is Hong Kong. So this is basically warm and humid climate, where you can see the temperatures are basically ranging between 16 degrees Celsius to about 30 degrees Celsius in summer. And here again, the variation in relative humidity is similar to what we saw in Vijayawada. This is somewhere between 65 to 76%. But then here the comfort conditions are comparatively better to Vijayawada, though the temperature ranges are 30 degrees and the relative humidity is similar to what we experience in Vijayawada. Here the temperature ranges are different, but then the higher wind speed, 3 to 4 or 5 meters per second, causes enhances the comfort. So you can see here the comfort range is a lot of lines within the comfort range are mainly because of higher wind speeds. So here the issue, what we need to look at it is not just the values, it is a combination of the temperature, the humidity and the wind speed. In cold climates, the wind speed creates a lot of wind chill index, but in hot climates, the humidity and higher temperatures lead to a lot of discomfort. So I think these things we have already discussed. The mean radiant temperature, basically when it comes to outdoors, during daytime we gain a lot of temperature, like Dr. Fayez was mentioning, during daytime the MRT increase. So it is basically the reflected radiation that one perceives during daytime. That's basically, so that would create a lot of heat gain in human body. During night, in the absence of solar radiation, we will lose heat to the atmosphere. So this is important. So mean radiant temperature is an important index which we need to look at, because that would define whether we are going to gain heat or lose heat to the environment. And as I mentioned, the temperatures, though the temperatures, if you see here in all three cases, the temperature is only 20 degrees Celsius. But the weather at that particular time. So this MRT also predominantly based on the weather condition on a particular day. So if you see at 20 degrees Celsius, if it's cloudy and calm, we would feel the same temperature. But the same 20 degrees Celsius, when we have higher solar radiation, which would result in higher MRT, which would result in heat gain, though there is no wind speed, we would feel a temperature of about 30 degrees Celsius. This is basically the our comfort index in terms of PET. So the higher solar radiation, we would gain a lot of heat. So we would feel as if it is 30 degrees Celsius. Similarly, with 20 degrees Celsius, when it is cloudy and if it is windy, then we would feel, though it is 20 degrees Celsius, because of higher wind speed, we would expect as if it is 15 degrees Celsius. So it also depends, the comfort also depends on the weather condition on that particular moment. So that also affects our comfort feeling or comfort sensation. So basically these uh, outdoor thermal comfort studies, I think we have there are a lot of studies that have been done in terms of field surveys, then field measurements and simulation, which we have seen in all these 4 days. Here, these are the threshold values that have been. So, how do we feel? Because the thermal sensation analysis in indoor differs from that of outdoors. So, we can here you can see this is a standard threshold values defined by Matsarakis. Basically, here it ranges from less than 4 to 41 degrees Celsius. Anything beyond 41 degrees Celsius is termed as extreme heat stress. Anything less than 8 degree Celsius is termed as strong cold stress. So the generally here it is defined as 18 to 23 is the comfortable range, but this would differ in terms of Indian cities. So this is a study that has been done by Kodarkar, wherein we have defined the comfortable ranges have been defined for Indian cities where we feel extremely hot, especially in the tropics. So it ranges from, wherein in the previous study it is ranging from about 18 to 23. Here we are just, they have found that the comfortable ranges vary between 26 to 30 degrees Celsius, wherein there is no thermal stress. Anything beyond 50 or 51, it is termed as extreme heat stress, wherein in the previous other studies in other countries, it was only 41 degree. So here, the heat stress varies from about 32 to 51 degree. It is categorized into slight heat stress, moderate heat stress, and strong heat stress. So these again, it varies based on the thermal sensation scale and thermal comfort scale, as well as thermal tolerance scale. So based on these, based on the number of points that you analyze, accordingly the ranges vary and it differs. So based on these, now we just go through some of the studies how these heat stress in outdoors could be mitigated through some design strategies. I think morning Professor Matt has given an elaborate indication of these landscape strategies, wherein these impacts, so if you see having a ground cover, I think even in Dr. Fay's study, we just realized the ground cover could not provide a lot of comfort. So the impact of ground cover is only to a range of about 10 meters, wherein the impact of group of trees and shrubs, it can impact the microclimate up to a range of about 60 meters. Similarly, the materials, I think yesterday we had Professor Matt presenting on a lot of these cool materials, how these, there were a list of 9 phase of materials which he discussed. So these materials used in pavement can also vary the outdoor thermal comfort. So, and the ranges varies from local to city level. So integration of artificial structures like green wall, green roof, fountains can affect at the local scale. At the street level, we can have the height to width ratio, which can impact the wind movement within the street level. At the public parks or open spaces, the tree canopy, ground cover, water catchment features at the urban greening level. And then at the city scale, the reflective materials on roofs, which we had seen several such case studies which was presented by Professor Matt yesterday. So these will have an impact at the city scale. So the intervention can range from local to city scale, which can have a significant impact on cooling. Similarly, at the neighborhood level, we can either have canopies. I think we did see Professor Dr. Fayez mentioning about spacing between tree canopy. So that also matters because that also reduces the sky view factor. So which will also have an impact on thermal comfort. The portion of the um, uh, canopy that shade that will have better cooling when compared to areas that are completely exposed to sun. So then these kind of temporary shading structure, yesterday Professor Matt was mentioning about the dynamic shading structure, movable shading structure. We can either have static or dynamic, and the shade of these structure which falls throughout the day varies from morning to evening. So you can create these areas can be shaded. It cannot be shaded. It will not be shaded throughout the day, but at some point of the day, the shade keeps on moving. So the pattern of usage of these outdoor space can also vary based on the shading ranges. So exposed areas again can be enhanced by means of introducing water features so that it can add some kind of humidity into the atmosphere. Um, there are also other studies, like we had discussed a lot of these in hot and arid climates. Here again, strategies from 50% grass along with trees, 50% grass with 25% trees, and 50% grass with 50% trees, and 75% trees are underlined. Here again we can see when getting into these are basically simulated studies using NVMet software. We did mention these on-site measurements are important. Dr. Fayez also mentioned that these are important when we use simulation studies because it requires the validation is important. So when we simulate in softwares, we have to collect on-site measurements and validate those. Different strategies were analyzed, and the best strategies that improves the outdoor thermal performance were analyzed. Again, the parameters that are analyzed are like varies from individual meteorological parameters like air temperature and humidity, and also the comfort indices in terms of MRT, PET, UTCI, all that can be analyzed. So again, these are different strategies wherein we can see first in a neighborhood they just improved only 50% grass cover. The second strategy 50%, the scenario basically 50% with 25% green cover. Then the third one 50% ground cover and 50% green cover, and 50% ground cover and 75% green cover. So they performed this in a neighborhood, and the selected trees basically depends on the parameters that they have chosen are leaf area density, foliage height, leaf area index, and albedo. So these were selected, and then within these they've selected different within the neighborhood in different scenarios. They've selected 4 points. One location where they had pavement and tree only on shade on one side. Another location wherein it is between two building surface with asphalt road. Another location between two buildings but it has a pavement. Then the location where there is a green cover, grass, wherein the number of trees, the tree canopy has been increased again between. So they try to analyze these. So this is at location R1, how it performed in all three scenarios that were analyzed. So we can see that this is again our temperature reduction in terms of Kelvin. The temperature reduced during nights till about 6 a.m. Then it started increasing, and this again depends on the sun angle. This reduction after 6 a.m. to 12 a.m. Depends on the shade, mutual shading between buildings, and also depends on the sun angle, and it just elevates in the afternoon and then it decreases. And this varies with point to point depending on the shading condition in the night. So here you can see it reduced to about 0.2, wherein here the reduction is only till about 0.4. So this is R2, which is this location, because again the tree did not reduce it. Here it was just open. So the reduction we can see up to 0.2, and there are some spaces of which are exposed to the sky, so it can radiate back. So again you can also see the reduction here. When it's here it is somewhere around 0.5 reduction in the night, ranging from 0.2 to about 0.5. As the density increases, you can see as the density increases, the this is wherein 50% grass cover and 50% tree cover. So the temperature reduction is also enhanced mainly because of increase in relative humidity, this being an arid condition in Egypt. So these are different scenarios and different points. So you can see a reduction here of about, this is the base case, and you can see a reduction of from about 70 degrees to about 55, around 15 degrees Celsius reduction is there, but the behavior differs. Here it is only one side tree and it is a pavement. Here it is two side tree with asphalt. So here the second scenario did not perform well, but the other three scenarios performed well. Wherein here, which has ground cover and then trees with ground cover and trees with pavement. So the ground cover matters a lot in terms of heat that is being radiated back into the atmosphere. Then these are some of the studies that have been done in Chennai. Now we'll just move on to some of the studies that have been done in India. So this is a study that was done in Chennai, a region called Tyagaraja Nagar, which is a mixed residential neighborhood. Here, similar to Dr. Faiz, we had taken 3 LZZ locations within Chennai, wherein this we try to analyze how the building regulations impact outdoor comfort conditions. So the first case provided the existing building regulations. So we just assumed that maximum built up with the existing building regulations. Then the same thing was introduced with increasing height and reducing the plot coverage. So that was the development regulations in Chennai was modified in 2019. So we tried to see what would be the impact of this modified building regulation, which had increased building height and increased FSI, while the plot coverage was reduced. So that gave way for a lot of open space at the site level, wherein here we considered the existing vegetation itself. And in case 3, we increased the open spaces that were available at the plot, converted 50% of that into vegetation and trees, which are planted at an interval of 6 meter to 9 meter. So this increased the permeable surface fraction and the green cover fraction. So these were the 3 scenarios that were analyzed to find out which had the maximum enhanced outdoor thermal comfort conditions. So these were the 3 locations. And then in the first case, we could see these are the parameters as per the LCZ classification. So we analyze the sky view factor, the aspect ratio, the building surface fraction, impervious surface fraction, pervious surface fraction, height of roughness element. So if we see this, the height of roughness element increased with building height. So if you see here, the height of roughness element are lesser because wherein the building heights were much less. In case 2, the building heights were increased, but then vegetation was not increased. So the roughness element increased in the case 2, wherein here the building heights are increased and plot coverage increased, but retaining of existing vegetation. In case 3, the green surface fraction was increased, which increased the permeable surface fraction. So you can see that the permeable impervious surface fraction is the pervious surface fraction is increased significantly from the case 2, and the impervious surface fraction has reduced from case 2. So this enhanced the comfort. So we just try to analyze this, and these were plotted. So based on this analysis, so each the sky view factor again varied because as the building height increases and the plot coverage reduced, the view to the sky also increased. So this is location A in the 3rd level with lesser building and increased plot cover, the view to the sky was increased. So we can see that in the first case, which was the base case, the number of hours of extreme heat stress, this extreme heat stress is as per greater than 50 degrees Celsius, which is based on PET values. So you can see number of hours of heat stress in the base case was just 7 hours in the base case, in the improved case with 50% conversion of the plot area into grass cover and permeable surfaces, the extreme heat stress is completely reduced, and it is just gone into the moderate heat stress of 46 to 50 degrees Celsius, which was considered as moderate heat stress as per the recent study in India. So this has reduced the number of extreme heat stress in all three locations. So even in location B, which had just 2 hours of extreme heat stress, is completely reduced, and it doesn't even have moderate heat stress. It just reduced to only so this has significantly reduced to moderate heat stress or strong heat stress. So you can see that the duration of extreme heat stress has been significantly reduced in the modified building regulation by increasing the building height. Again, this depends on the compactness of the neighborhood. If it is compact, then that would vary. So if you see here, the LCZ classification varied with varying the building regulation. This was open mid-rise, and then location A remained open mid-rise, but in location B and C, which was a compact low-rise in the existing condition, was modified to compact mid-rise because of building height, and which was an open low-rise in location C has modified to open mid-rise because we had increased the building height but then increase the pervious fraction. So the local climate zone classification also varied. So that also will have an impact on the enhanced comfort conditions. So the next study is basically, this was done at Ahmedabad, wherein we did try varying some of varying the building heights in gated communities. So there is in Ahmedabad, especially near Charodi region, where the high-rise buildings started cropping up in the recent decade. So we analyzed what is the aspect ratio in the high-rise building, high-rise housing, which is a gated community, and we categorize them into 3 aspect ratio ranges. So aspect ratio range of 1 to 1.5, then aspect ratio range 2 is 2 to 3, and aspect ratio range 3 is 4.5 and 5, and we found majority of the buildings fall under the category of aspect ratio range 2 to 3. So we chose one of the high-rise housing in that range 2 to 3, and we measured on-site data, and we tried to validate through NVMET simulation, and we found a good correlation. Then we varied various scenarios by varying the building height. First, we tried to vary the building heights in northwest and southeast orientation. Then we modified the variation in southwest and northeast orientations. Then we introduced shading blocks between buildings. It could be, this was in terms of just a pergola or a shade. It is not a floor, it is just a shade between the buildings. Like because we did realize that shading enhanced outdoor thermal comfort. Then we introduced it in the northwest southeast blocks. Then the similar thing was introduced in the southwest northeast blocks also. Then we varied all the heights of all the buildings, and we just analyzed these in NVMET simulation. We did do the analysis for both critical summer and winter conditions for the entire day. So this realized, if you see, the first one was just higher building in southwest northeast, and the second one is north west and southwest southeast. So the third one with shading, then with shading in the other orientation. So we did find from the base case had about 6 hours of extreme heat stress, that reduced to about 5 hours of extreme heat stress, though it is just 1 hour. But then the variation, if you see, it has reduced to about 2 degrees Celsius. So from 52.4, it reduced to about 50.4, which is a significant reduction in terms of PET values, 2 degrees Celsius. But the same thing in winter, when we saw, The winter also, they did have extreme heat stress of about 5 hours, which was significantly reduced to 3 hours in scenario 4 and 5. But then if you see scenario 3, though it had 6 hours of extreme heat stress, but in winter it was quite comfortable. So overall, scenario 3 performed better, but then here again we had a similar reduction of about 2 degrees Celsius, though it is the number of hours is same, but then reduction is significant. So these analysis has to be done for both summer and winter. Doing it only for summer may not be effective because we have to take it for a annual basis. So this was done, and then we did try to, using the best performing scenario, we did modify the same thing. So the existing was uniform height of all 4 blocks. Then we oriented in the best orientation with this northwest southeast. Then in the we just increased the height in the northwest, and then introduce a shading block in the northwest, introduce another shading block in the southeast. Then we perform the final. This was the proposed scenario. So this again was analyzed between the other case scenarios, and this proposed scenario which varied building height in all. Here, when we vary the building height, there was just one consideration was considered. We had kept the FSI constant. We did not increase or decrease the FSI. FSI was kept constant. Only certain relaxation in building height was given. So normally in development regulation, there will be a restriction on maximum height to be built. So this we just relaxed to find out how this could enhance the comfort condition. It was not maintained as per the development regulation, but FSI was kept constant. Certain amount of relaxation were given in building height, but we did consider the air corridor and all that. That was not, it was not in the air corridor. So the height were increased, but then FSI were kept constant. So the saleable area remained the same. That did not vary. So with that variation, we could reduce from about 6 hours of extreme heat stress to about 3 hours of extreme heat stress, and significant reduction in terms of 2 degrees Celsius in the PET. And it also had impact on moderate and see, there is an increase in moderate and strong heat stress because we had reduced from extreme heat stress has gone to moderate heat stress and strong heat stress. Similar analysis was performed for winter also, and we found that the scenario had just 1 hour of extreme heat stress, but then predominantly throughout the day this was comfortable. So based on this, we suggest that varying building height, but maintaining the FSI, which is in terms of asymmetrical canyons, depending on the location. Here in Ahmedabad, the northwest and the southeast orientation performed better. So these were the findings of the study. So we could see a reduction of PET from 53.7 degrees to 39.3 degrees. This is in winter and this is in summer. So this, and then because of the proposed this is in summer. So you can see this was reduced to about 39.3 degrees Celsius, and our MRT was significantly reduced. And even the PET in winter in the proposed state reduced to 32.7 from 59.7 in the existing scenario. So the proposal of 3:2 aspect ratio and northwest southeast orientation worked better in Ahmedabad scenario, but this would vary depending on the local geographic location and the wind direction. All that matters, makes an important needs to be considered for final recommendation as such. This is another study which was done in Vijayawada, which is again an hot humid climate zone, where we try to analyze the impact of sky view factor. Here also we vary the percentage of green cover and grass. Here we took 2 narrow, this is again a high-rise neighborhood wherein two pathways within the neighborhood which had a sky view factor of 0.224 and 0.342 vessel. This is the mean pathway and this is the space between buildings. We try to analyze how this could improve the thermal comfort conditions outdoor. So, is there some question or
Can take some questions actually. Anybody have questions? Ma'am's work is so we can ask questions, unlike Dr. Maths. So if you have any doubts, please feel free to ask.
any questions?
Yeah, no questions.
Can I continue?
Raghavi. Anybody? Raghavi, are you trying to ask something? If you're trying to ask, please ask or type in the chat box. Else, please mute yourself because we are not understanding whether you want to ask anything. I'm not able to understand. Either people, please either ask question or mute yourself because we are not hearing anything with clarity. Raghavi, Miss Raghavi Ilangovan, please mute yourself or ask your question. If you don't have a question, please mute yourself. The speaker is not able to understand whether you want to ask a question and then it is hampered. The talk is stopped now. Miss Raghavi, please mute yourself. Doesn't look like she wants to ask any question. Okay. No chat box. No.
Okay. Can I continue?
Yeah, we can continue.
Yeah. So this study again, we analyze different scenarios and also we analyze different orientation of this particular neighborhood. This is the typical which had 5 blocks and a club house. Actually, the existing had 6 blocks. We removed 1 block to create space for open space there. So this is the kind of scenario that we analyze. The first scenario was 20% tree cover. So we analyzed in different
Madam, please, Miss Raghavi Ilangovan, please mute yourself. Sorry, madam, continue and write in the chat box.
Yeah. So
she's
we
muted.
did analyze 20% tree cover with different orientation, rotating this to identify which orientation works the best. And then we analyzed the same for various parameters like air temperature, mean radiant temperature and PET. And we found that the 225-degree orientation, that is the south, 225-degree orientation, which is the southwest orientation, worked the better because that created mutual shade between buildings, so which enhanced the thermal comfort. So then we did analyze for 50% tree cover. Similarly, we oriented and we found here the 135-degree orientation, that is basically the southeast orientation worked better. Similarly, 70% grass cover. We did not go in for 70% tree cover because that completely covered the sky. So we tried to analyze. This was taken from previous literature. Then we analyzed 70% grass cover. So this again gave 225 as the best performing orientation. So based on this, we did analyze PET. So we can see that 50% tree cover and 20% tree cover more or less perform better. But then here the reduction is significant from 52 to 48.2. So it's roughly around 4 to 5 degree reduction was there in 50% tree cover, wherein 20% tree cover we could get 2 degree reduction. Here if you see 70% grass cover, there was no reduction. Instead, it increased the PET values as we saw in Dr. Fai's study also. So the grass cover, suggesting grass cover actually increases the PET value, and it also increases MRT value. So it is always better to go in for trees, a combination of tree shrub, but then grass cover beneath the shade may work better, but then exposed to sky may not work better. So this is the analysis, and we can see that a temperature reduction of 1 degree Celsius up to 1 degree Celsius was derived from 50% tree cover, and a temperature reduction of only 0.1 degree Celsius was there in terms of 20% tree cover, and the temperature increased in 70% grass cover. Similarly, in terms of MRT, there is a reduction of about 4.75 degrees Celsius in terms of 50% tree cover, and it was 3.25 degrees in 20% tree cover, and the temperature increased in 70% grass cover. Similarly, a reduction of 2.5 degrees Celsius was observed in terms of 50% tree cover in PET, and 1.6 degrees Celsius in terms of 20% tree cover, and the temperature increased in 70% grass cover. So the study, after doing this, we realized that a reduction of 1 degree Celsius with 50% tree cover, how this could impact the energy consumption in indoor. So we just model using this meteorological condition at this scenario. We reduce the values of our temperature by 1 degree in the microclimate in design in the EPW file, and then we ran the simulation in Design Builder to find the energy consumption, the indoor energy consumption pattern during summer and winter. And we categorized the building into 3 levels: the lower levels, middle floor levels, and upper floor levels, because the energy consumption pattern also varied with the number of increase in floors. So we can see that during summer, though the reduction, this is just done for 1 day, but it has to be done for monthly basis. We just ran the simulation for 1 day for want of time, but then this, if it is run for a month, then this can be run better. So here we just multiply that into number of units for a monthly basis, and we found that this is the saving on a monthly basis at different floor levels. Though this is lesser, the cost during summer depends on the total number of energy consumed per month. So energy units consumed, as the number of unit increases, the cost is also increased, because of which the this is the savings that we get got during the study, and it varies, and it is, the saving is much higher at higher floors when compared to lower floors. Similarly, in winter, the savings were much higher. So the reduction in number of units is much higher, but it is more or less the same in all the floors. But since in winter the total number of units consumed are much lesser when compared to summer, the cost reduction is per unit is much lesser. But then if you can get much better significant reduction in winter when compared to summer, because the summer temperatures in Vijayawada are quite high. It ranges from about 38 degrees to about 43, 44 degrees during daytime. So without air conditioning during daytime, it is not at all possible to stay indoors. Because of that, the summertime savings are much lesser. But in winter, if the microclimate is modified, that can enhance the energy consumption, that can reduce the energy consumption pattern, and it can enhance the energy savings. So we can save much because the summer temperatures in Vijayawada is somewhere around 34 degrees Celsius. And if that can be reduced by about 1 degree Celsius, then it will have significant impact on energy savings as such. So this was another study done at Vijayawada. So we can see the savings in terms of, so the middle floor had better savings in summer, wherein the upper floors had higher savings during winter. So here, as far as Vijayawada is concerned, the 135-degree north orientation, that's basically the southeast orientation, enhanced comfort. That's mainly it minimize sunlight exposure and it maximize the wind speed. Being hot and humid, the wind speed played a significant effect in enhancing outdoor thermal comfort. And generally, these gated communities had a maximum building height of 24 meters. So a 13-meter spacing was suggested between buildings, which will include 2.5 meter spacing between buildings and the vehicular movement or the road. So that can provide, that can integrate greeneries or vegetation or trees within the gated community, which can enhance the thermal comfort conditions, especially in the outdoor, which will again have an impact on indoor energy consumption also, that can be reduced significantly. So that was the finding of this particular study. And there's another study which was done at Ahmedabad, especially in low income settlements. Here, it was found as a hotspot in Ahmedabad. We analyzed 4 different clusters here, wherein we tried roof level, pavement level, and at the wall levels. So we modified different materials in the roof, which had higher albedo of 0.7 and 0.8, 0.95. Then we also had medium albedo in terms of 0.3, 0.3. These are the different materials that we use. So we mainly, the study had concentrated on higher albedo. So we just categorize HR indicates higher albedo, M indicates medium albedo. So L indicates low albedo. So these were the options that were used in pavements, walls, and then roofs. So then we tried to replace it with the existing condition, which had brick wall and GI sheet roofing, and some of them had asbestos, cement, and concrete pavement and bare soil. These were the existing conditions. So we did simulate different conditions here. So here, the first case was medium albedo in wall, medium albedo in roof, and low albedo in pavement. And these were the mean radiant temperature values. So here, these options or scenarios which had medium albedo in wall, lower albedo in wall perform better with lower pavement. So here we realize that the walls and pavement should have predominantly lower albedo as they reflect heat onto the streets. And the roof, since this is a low-rise development, this suggested medium albedo is much better. So if you see here, from here there is a reduction of about 1 degree, but then though 1 degree reduction is very less, but we can see this reduction in terms of MRT was reflected radiation, it was much better. So the other three clusters wherein we can see here the medium albedo in wall, the medium roof and medium pavement perform better. So we can see that the maximum temperature, the ranges have predominantly, these are just moderate with just 1 hour with extreme heat stress. So we are just looking at the number of hours of extreme heat stress, reduction in that, because you cannot reduce the heat stress throughout the day. So the intent is to reduce the total number of hours of extreme heat stress rather than looking at removing heat stress from that location. That is not possible with the higher temperatures and humidity that are experienced in tropical regions. So here we were able to reduce the extreme heat stress to just 1 hour from the base case, which was approximately 4 hours. So that is the kind of approach we had done it. Here again, in this particular cluster, we could again medium albedo work better. So this study suggested that low-rise informal settlements going in for higher albedo as they reflect heat into the atmosphere and which are trapped. It acts as a heat trap, and due to convection at the lower level, the street level temperature or the mean radiant temperature comfort level was very hot. So if in high rise, then going for higher albedo is better, but in low rise, especially G+1 structure, going for higher albedo in the roof may, due to convection, it might increase the heat sensation on the street. That was the finding in this particular study. Yes, I think with this, I would stop here. Thank you for your attention. If there are any questions, I can just.
Anybody has any queries, any questions, or any aspects to discuss?
Yeah, good afternoon.
Good afternoon.
Yeah, I have one question actually, ma'am. You have talked about the indoor thermal comfort and outdoor also.
Yes.
In Indian context, do we have any national standard for indoor thermal comfort, like say in RCC roof or tile roof or tin roof? The temperature should be range between this degrees Celsius, and that need to be followed by different departments like housing department.
No.
Do we have? Yeah.
No, we do have standards in terms of thermal comfort range, indoor thermal comfort range. But in terms of temperature of materials, we don't see, this is basically defined in terms of thermal comfort range rather than the temperature on materials. You're talking about the surface temperature and different
Yes.
materials. Because that does not define that, because again thermal comfort depends on the overall comfort range. So we'll have to follow the thermal comfort range. IMAC stipulates operating temperature for various cities. So based on that, based on IMAC only, we analyze these studies. So we did, based on the operating temperature range, we were trying to see whether modifying these material assembly in the building envelope can enhance the comfort within, can bring down the comfort within that comfort range. That is the intent. But in terms of surface temperatures, there is no standard as such. But in terms of comfort ranges, there are standards. ASHRAE standards are followed, and for Indian cities, IMAC is generally adopted.
Okay, thank you.
I think so Vijay Lakshmi can add on to it because it's on indoor thermal comfort.
It's your day, ma'am. Enjoy. I'm like dumbfounded after the first class.
Yeah. How to select the appropriate thermal comfort index for city scale that works both indoor and outdoor. See, the thermal comfort index, it depends on the climate type basically. So not all thermal comfort indexes suit the different climate types. So for especially humid climate, the index that includes humidity as an aspect need to be considered. So generally for tropical cities, PET, UTCI are generally adopted for outdoor thermal comfort, as well as in terms of indoor thermal comfort, it is basically the operative temperature which we use. Yes, Aishi, did I answer your question? Miss Aishi?
Yes, thank you, ma'am. Yeah. But, ma'am, in addition to that, I also wanted to know, say, if I'm comparing between the city level phenomenon of across different climate zones, would I need to calibrate those values? so as to say this is equivalently comfortable or something?
Within the same city, you are trying to say at different neighborhoods?
No, yeah, that, and also for different climate zones, for cities in different climate zones, if I am to compare the comfortable conditions.
So different climate zones will have different comfort ranges. So you'll have to first identify the comfort ranges for that particular climate zone or for that particular city. And then you'll have to compare your results with that particular comfort ranges. For example, in Vijayawada, even 32 degrees, 31.5 is considered as comfortable in terms of outdoors. But for indoors, we don't go beyond 28. So it all depends on the comfort range. Cities and the type, whether it is in indoors, it depends on whether it is a naturally ventilated building or if it is a conditioned space. So based on that, the comfort ranges differ. So based on your study condition and based on your assumption, you'll have to derive those comfort ranges and then compare your findings.
Okay, thank you, ma'am. Yeah, got it.
Any other question? Dr. Vijay Lakshmi, Dr. Prashanti,
Yeah.
if there are
Yeah.
questions,
So,
can we mind them?
yeah, okay. Since there are no more questions, thank you, Dr. Lily and Dr. Faiz. Thank you so much. And we will meet again tomorrow, which will be the last day of the CAN program. It will be the 5th day. So please be on time. Otherwise, you will miss important things that are told. Okay. So be on time and we will meet tomorrow. Thank you. So tomorrow's session starts at 11. It's only by sir and it is 11 to 1. So be on time tomorrow. Thank you. So join at 11 o'clock tomorrow, 11 to 1, and then we'll have a small valediction which is online. Thank you, Brindaji. Thank you so much. Bye. So I will log off. Thank you.